Good morning, everyone. Welcome to our lecture for our inorganic chemistry course. So now this is our last lecture before we have our exam next Friday. So today we will be finishing our course, and then we will finish our discussion on coordination compounds, which will mark the end of all the contents that we wanted to cover. So just as a reminder, we will see everybody. We will be all together in Zoom on Friday at 12:15, and then I will send you guys the exam here, and then you guys can complete the exam and return to me by 2 o'clock. Okay. So if you have any questions in the meantime, please let me know. So in the last lecture, we finished the discussion on the crystal field theory and ligand field theory for the description of bonding in metal complexes having a variety of geometry. So we saw that that the ligands in the crystal field theory are approached as negative point charges that cause the splitting of the energy levels of the d orbitals of the metal into different sets of energies, and this is explained due to the repulsion between negative charges, and these splittings is what dictates properties in metal complexes and coordination compounds. So we saw how those splittings are for the octahedral complex, why this happens for the octahedral geometry. And then we saw that we can also distort the octahedral to have this tetragonal distortion, to have this kind of splitting of the d orbitals in a tetragonally distorted complex relative to the octahedral complex. And if we continue this distortion to the point in which the ligands along the z direction are removed, then we are left with a square planar four coordinated complex, which has these corresponding patterns for the splitting of the d orbitals. And for the tetrahedral complex, we saw that as opposed to the case of the octahedral, in which the complex is approached in which the metal is in the center of the x, y, and z axis. For example, in the octahedral, we place the four ligands are placed using this coordinate system in between the axes. So we have this kind of splitting of the d energy levels in a tetrahedral crystal field. And then we saw that in the ligand field theory, we can apply molecular orbital theory to the ligands and d orbitals of the metal to explain the occurrence of pi interaction that can lead to the decrease or increase in the crystal field splitting relative to the scenario in which we can have only sigma bonding to the description of the complex. So we saw sigma and pi bonding, and then we saw that with the ligand field theory, we can explain the pi bonding in complexes and also explain the trends that we see for the crystal field splittings or the ligand field splittings in the spectrochemical series. Okay, so let's use this knowledge now to study, for example, how we can understand the electronic spectra of the complex, because the electronic spectra is a result of electronic transitions that occur in these complexes and that lead to absorption of ultraviolet and visible light, for example. And interestingly, the magnitude of the ligand field splittings that we observe, therefore, are directly related to the energy of these electronic transitions. However, in metal complexes, we can also have repulsions between the electrons in the metal. So therefore, these electron-electron repulsions also contribute to the electronic spectra. So the electronic spectra that we see is a combination of these ligand field splittings and also the electronic repulsions. And then we will discuss the spectra first of free atoms to understand how to take into account these electron-electron repulsions. And then we will see what kind of energy states these atoms can possess when they are placed in an octahedral field. And then we will see how these energies can be described for various ligand field splittings, various electron-electron repulsion energies to understand the electronic spectra of the coordination compounds. Okay, so here we have an example of the electronic spectra of a complex containing chromium 3+, right? Which is a D3 complex. So here we have octahedral geometry. So we have this kind of splitting of the D orbitals. So here we have energy. So if it's a D3 complex, we would see, or we would say that this is the electron configuration of the on the D orbitals of the metal here. But then, interestingly, we can see here, this is the electronic spectra, because based on this electronic configuration, we would expect simply one band, which is related to the promotion of the electron from this, or one electron from this level to this level. But we can see here that we can have several types of bands that correspond to absorption of energy in the spectrum. And we will understand why we can have many of these signals. So first, in this region here, in which we have higher wavelengths or lowest energy, we have very weak bands that they are spin forbidden transitions, that we will understand this in the next slides. In this region, we have these two bands have intermediate intensities. These are called the spin allowed transitions, and these are transitions between the T2G and the EG level, right? As described here. So, and then here in this position of the spectrum, we have what we call charge transfer bands, which are very intense. So the question is, how come in this region that comprises transition between the T2G and the EG level, how come we have two bands instead of one? And this is because we have electron-electron repulsions. And then we need to understand why these electron-electron repulsions lead to this more than one band, for example. And to understand this, we need first to consider the spectra of free atoms or ions before we consider the spectra of the complexes. So for example, considering now, let's suppose we are talking about free atoms or free ions, so no complex, so just the metal atom or ion. So when we do an electron configuration, right, the electron configuration is not a complete description of the arrangement of the electrons. So for example, if we get a 2p2 configuration, for example, right, the electrons may occupy orbitals with different orientations of their angular momenta. So if we consider the angular momentum here, or the quantum number for angular momentum, we have this, for example. So the electrons can be like this, or like this, or like this, right? So there are many possible arrangements for these two electrons in the p orbitals. So, so just saying 2p2, this will not tell us like which orbitals or what's the orientation of their orbital angular momenta that the electrons have. And then also it doesn't say about the spin orientations of the two electrons that can be, for example, paired if it was like this, or it can be unpaired if one electron is here and one electron is here, for example. So the overall spin or quantum number for spin can be plus 1/2 or minus 1/2 for each one of these electrons and the respective combinations. Therefore, we can have very different states for a total orbital and spin angular momentum, in which we can have the different combinations or different occupations of these orbitals with different values of orbital angular momenta and different values of total spin. All right? So one important thing to understand is that these different ways by which the electrons can occupy orbitals specified in a specific configuration, such as the 2p2 that we discussed. So the different ways in which the electrons can be present. So let's draw here various ways, for example. So it can be like this, it can be like this, it can be like this, for example, right? So here the ML is 1, 0, -1, and here, yeah, so this is for ML, and then this is like for the spin here is plus 1/2 and plus 1/2, and here's plus 1/2 and minus 1/2. So for example, so the different ways, so here, like the different ways in which the electrons can occupy these orbitals specified in the configuration are the microstates of this configuration. So for example, one microstate for the 2p2 configuration is this. So here we have the value of ML. And here we have the sign of the spin. So this microstate means that one electron has ML plus 1, the other one and has spin up, and the other electron also in the microstate in the ML plus 1 and has minus sign for the spin. So this microstate is represented by this configuration. This microstate, for example, corresponds to this configuration. So this notation, therefore, like in this case, both electrons occupy an orbital with ML plus 1, but do with opposite spins. Here, oh no, there's a -1 here. So actually, this electron is here. So in this microstate, both electrons have spin up configuration, but one occupies the 2p orbital with ML -1, and the other occupies the orbital with ML equals to 0. All right. So these different arrangements or these different microstates will have the same energy only when the electron-electron repulsions are negligible. But these electron-electron repulsions are strong in this case and cannot be ignored. So we can have when we have these different configurations or these different microstates, the microstates that correspond to different relative spatial distributions of electrons will have different electron-electron repulsions and therefore different energies. And when we group together these microstates that have the same energy, after considering this effect of electron-electron repulsion, then we have what we call terms or energy levels that are distinguishable spectroscopically. So energy levels in which we can observe transitions between, or electronic transitions between these levels. Because after electron-electron repulsions are taken into consideration, when we group these different configurations on microstates together, so the microstates that are grouped together having the same energy are called terms, and then they can be distinguished spectroscopically because they will form one energy level. All right. So when we consider light atoms in 3D series, an important property of the microstate that determines the energy of that microstate is the orientation of the spins of the electrons. So this is the first factor that influences the energy, the relative orientation of the spins, and then after this, the relative orientation of the orbital angular momentum, as both of these things will influence the electron-electron repulsion. So we can identify the order of energy of these terms by sorting or checking which microstates are there according to the total spin quantum number S, which is determined by the relative orientations of the spins, and then according to the total orbital angular momentum, which is determined by the relative orientation of the individual orbital angular momentum. So we can find these values of L, total angular momentum, and the total spin quantum number S using this Russell-Saunders coupling, in which we can identify the values of L and S that can arise from combining the orbital and spin angular momentum of the individual electrons. So supposing that we have two electrons with these quantum numbers, the possible values of L and S vary from L1 plus L2 until L1 minus L2, and S varies from S1 plus S2 until S1 minus S2. So for example, if we have D2, L varies from 4, 3, 2, 1, 0, and S 1 or 0. And from analogy with the notation S, P, D, and so on for orbitals with L0, 1, 2, the total angular momentum of an atomic term is denoted by the equivalent uppercase letter. So if L is equal 0 is a S term, if L equals 2 is a D term, okay? So for example, in the D2, as we saw, these are the L and S values that are possible, and the total spin is actually reported in terms of 2s plus 1, and 2s plus 1 is called the multiplicity of the terms. So we have these values for the multiplicity of the terms for these different values of S. Okay? So this is important to understand. And when we are talking about notation, so we have the term symbol and having the spin multiplicity written as a left superscript to the letter representing the value of L. So, and the entire label in this case is called a term symbol. So the term symbol triplet P, so here triplet denotes a term in which we have L equals 1 and S equals 1 as well. Okay? So once we know the values of L and S that can arise for a given configuration, as we saw for D2, so we can identify which is the term having the lowest energy using the Hund's rules, which help us to approximate what is the terms that will have lowest energy because of the lowest electron-electron repulsion. So for example, the first rule is for a given configuration, the term with the greatest multiplicity will be lowest in energy. And for terms with a given multiplicity, the term with the greatest L lies lowest in energy. And the reason for this is that when the angular momentum is high, electrons can stay away from each other and therefore experience a lower repulsion. And the same thing applies for the greater spin multiplicity, because this means a higher amount of unpaired electrons, which therefore would lead to lower repulsions as well, or spins parallel configurations. So if we have a D2 configuration, actually, we can have all these microstates as present in this table for L equals 0 or 1, 2, or 3, and 4, for example, and for the different values of MS. So here is the total spin, and here the total value of the orbital angular momentum. And here, for each one of the terms of this D2 configuration, we can see the number of microstates that each term has. All right, so for example, the singlet S comprises only one term, while the triplet F comprises 21 microstates. So according to the Hund's rules, if we have these terms for the D2 configuration, we can predict the order to be this one, the order of energy. And this is close to what's observed spectroscopically. There is a difference here for the D and P terms, but the important thing is that the ground term is the same. So for a highest multiplicity, and then for a given multiplicity, higher value of L. All right. So when we are interpreting this electronic spectra and we want to see what are the spectroscopically distinguishable energy levels, all we want to know is the ground term. So it's very important to be able to identify what's the ground term. And this, according to the Hund's rules, we can do this easily by identifying the microstate with the highest value of spin angular momentum. So this will have the highest spin multiplicity of that configuration. And for that multiplicity, we then identify what's the largest value of orbital angular momentum that will be possible. So for D2, we have these energies of the terms, for example, and here is a presentation of the energy of the terms for a D3 configuration, okay? So this is only for the free atom or for the ion, and then later you see how to include the effect of the ligand field as well. And then these different terms of a configuration, they have different energies because of the electron repulsions. And now, like, how can we understand these electron repulsions? So to calculate the energies of these terms, we have to evaluate these electron repulsions energies, and they are evaluated like as complicated integrals over orbitals that are occupied by the electrons, and then all these integrals can be calculated, but what is interesting here that we can make an approximation in which all these integrals can be collected together in 3 specific combinations, and the repulsion energy for any term of any configuration can be expressed as a sum of these 3 quantities or these 3 specific combinations. So the 3 combinations of integrals are called Raka parameters, and they are denoted as A, B, and C. A here, the Raka parameter A corresponds to an average of the total inter-electron repulsion, and B and C relate to the repulsion in energies between individual electrons. So all these Raka parameters A, B, and C they summarize the effects of electron-electron repulsion on the energy of the terms that arise from a single configuration. So they are a quantitative expression of the ideas behind the Hund's rules that we described briefly. And when we have the terms for a specific configuration, so each term will have an energy that might be expressed as a linear combination of all the three Raka parameters to explain or to account for their energies. So for example, for the D2 configuration, so we have the different terms and the energies of these terms are therefore expressed as linear combinations of two or all Raka parameters that describe these electron-electron repulsions. So if we go back and take a look at the electronic spectrum of the complex, here in the case, chromium 3+, that it's a D3 complex. Well, we have 3 electrons in the T2G level and 3 orbitals in the T2G level, which has 3 electrons, and 2 d orbitals in the EG level. So for example, we have dxy, dxz, and dyz. So here in the T2G level, we have dxy, xz, dxy, and dyz orbitals. And here in the EG level, we have dz squared and dx squared minus y squared. So for example, if we have a transition from the orbital dxy to dz squared, this transition promotes an electron from an xy plane into an already electron-rich z direction, because we have electrons in all these orbitals, and the z direction already has electron density coming from dzy or dxz, for example. So this axis is electron-rich. On the other hand, if we have a transition dzx or dzx or dyz to the dz squared, this means that we are merely relocating an electron that it's already largely present along the z-axis. So you can see that in this qualitative picture, we can already expect that these two kinds of transitions would have different energies, okay? And these two bands are labeled as this label here, as represented here, and the second one here. So these labels here are the molecular term symbols, and we just saw the origin and what are the atomic term symbols. So, but here we have a complex and we are talking about the molecular term symbols, and they serve as a purpose, or their definitions and everything are very similar to what we just saw for the atomic term symbols, in which the left superscript is the spin multiplicity. So here, the superscript 4 denotes a quartet state in which S is 3/2. Remember that multiplicity is 2S plus 1. And the rest of the term symbol, here in this case, T and A, this refers, or this denotes, or this is a result of the symmetry of the complex. So this is a symmetry label of the complex. So in the free atoms or ions, we have S, L, P, F as analogy with the orbitals. But here, when we go from the atom to the complex, then we have this symmetry labels that is defined by the way in which these electrons are affected by the geometry of the ligand field, in this case, octahedral ligand field. So if we have a free atom, all the d orbitals are degenerate, and we need to consider only electron-electron repulsions to arrive at the relative ordering of the terms. If we have a complex, not all the d orbitals are degenerate, so they are split into two energy levels, for example, in an octahedral complex. And so we need to take into account the difference between the T2G and EG energy levels, as well as the electron-electron repulsions. So if we have the simplest case of an atom or ion with a single valence electron, the totally symmetric orbital in one environment, free atom, becomes a totally symmetric orbital in another environment. So the s orbital, which is totally symmetric in a free atom, will become, for example, a A1G orbital in an octahedral field. And then here, A1G, the important thing is that A1G here represents the totally symmetric configuration. So we express this change by saying that the s orbital of the atom correlates with a A1G orbital of the complex. So similarly, if we have the 5d orbitals of a free atom, they will, like, when we go from the free atom to the complex, they will correlate with a triply degenerate T2G and the doubly degenerated E2G sets in an octahedral complex, because they will be split into these kind of orbitals in an octahedral complex. So if we consider now a many electron atom, in the same way as we are describing for a single electron, the totally symmetric overall S term will correlate with a totally symmetric A1G term for the complex. And an atomic term having L equals D will be split into energy levels or terms having T2G and EG for the octahedral complex. And then here we are talking about total orbital angular momentum, because we have a many electron atoms. That's why we are using here now capital letters. So for atomic D term, we will have splitting into T2G and EG for a complex in octahedral geometry. So this is the correlation between atomic terms and the term for here, free atoms or ions, and here the terms into, or how they correlate, so the corresponding terms in an octahedral environment. So the S term correlates to the A1G term, P to T1G, D to T2G and EG, and so on. So now we have to consider how to understand these electron-electron repulsions in the spectrum of coordination compounds having electron-electron repulsions. This is quite difficult to take into account, but we can simplify this discussion considering two extreme cases. The first is the weak field limit, in which the ligand field, which is measured by the ligand field splitting parameter. So in the weak field limit, this ligand field splitting parameter is very weak. So this is so weak that only electron-electron repulsions are important. So if the field is so weak that only electron repulsions become important. And then we have the RACA parameters, B and C, that can fully describe the interelectronic repulsions. This is all that we need. These are the only parameters that we need in this limit. And then we can go to another extreme in which we can have a very strong limit, in which the ligand field is so strong that in this case, the electron-electron repulsions can be ignored. And in this case, the energies of the terms can be expressed only in terms of the ligand field splitting parameter. Then, after having these two extremes, we can consider intermediate cases by drawing a correlation diagram between these two limits. And we will illustrate this by considering two simple cases or species with D1 and D2 configuration. And then we will see how these ideas can be used to more complicated scenarios. So for example, if we have a D1 configuration, the only term arising from this configuration of the free atom, is the doublet D. So in an octahedral complex, this configuration is either T1 to G, which gives rise to this term, or E1G, which gives rise to this term. So, because in this case we have only one electron, there's no electron-electron repulsion to worry about. So here is the term in the free atom, and then this term, the D term, correlates to T2G and EG terms in the octahedral scenario. So there is no electron-electron repulsion to worry about. And the separation between these terms here is the same as the separation of energy between the orbitals. So is the same, this is dictated by the ligand field splitting parameter. So here, no ligand field, just electron repulsion, but in this case, this is not present here either because we have only one electron. And then here we have a correlation diagram connecting the two limits. So this correlation diagram is therefore something like this, in which the separation between these terms in the complex increases as the ligand field splitting parameter increases. So now let's see what happens for a D2 configuration. For the D2 configuration, the lowest energy term of the free atom is the triplet F that we also saw before. So we need to consider here, for the understanding of electronic spectra, only the transitions that start from the ground state. That's why it's so important to know only, like, to determine precisely what is the ground state of a configuration. So we need to consider only electronic transitions that start from this ground state. So only electronic transitions from the triplet F state. And we will discuss only the transitions in which there is no change in spin. Therefore, between terms of the same spin multiplicity. So there is an additional triplet term, which is the triplet P relative to this lower term, and the energies of these terms, like in this very weak field limit, in which only electrostatic repulsions are considered, are therefore 0 and 15B. So these are the energy levels represented in terms of the RACA parameters. All right. And then if we go to the very strong field limit, a D2 atom has this possible configuration. So 2 electrons in the T2G level, one electron in the T2G and one electron in the EG level, or the two electrons in the EG level. And then in an octahedral field, these configurations will have different energies as calculated here, as a function of the ligand field splitting parameter. So relative to the energy of the lowest term, this would be the ligand field splitting parameter, then 2 times the ligand field splitting parameter. And this is shown in this very strong field limit. So we have the energies for the very strong limit and the very weak limit, all right? So our problem now is to account for the energies that are there are intermediate cases, so not so weak field limit and not so strong field limit. So in these two cases, we can simply correlate the terms in the two extreme cases. So the triplet T2G configuration gives rise to a triplet T1G term, and this correlates to the F term of the free atoms, and the same thing is done for the other configurations. And this correlation diagram is called Orgel diagram as well, and this is very simple, but it's very valuable for the discussion of electronic spectra of complexes. And then we can also have these Tanabe-Sugano diagrams, which are diagrams showing correlations for all the spectroscopic terms that can be for a given configuration. So here we have the Tanabe-Sugano diagram for the D2 configuration, in which here we have field strength as expressed by the ligand field splitting parameter divided by B, in which B is a Raka parameter, and here the energy divided by B, in which B is also a Raka parameter. So we can, this is for D2, but we can have this for several, for all the electron configurations, and then we can see all the terms here for the free atoms and how they split and how, what do they become in the octahedral field, for example, and then the relative energies of the resulting terms. So we can see that the triplet F splits into three terms, the D1 into 2, and the singlet G into 4. So the term energies, therefore, are expressed as a function of the field strength using these diagrams showing these correlations for various field strengths and various electron configurations. Okay, yeah, we are not gonna enter into details of these Tanabe-Sugano diagrams because it's beyond the scope of this course, but you guys can feel free to read about it and how to use the Tanabe-Sugano diagrams to interpret the electronic spectra of complexes. And then another feature that remains to be explained is this intense shoulder in absorption, for example, that we saw for this complex having D3 configuration. So this high intensity suggests that this is not a simple ligand field transition. So it's not electronic transitions between the energy, the levels of the metal. And this is actually a charge transfer transition, which refers to transitions between levels that are, or between orbitals that are located predominantly on the ligand and orbitals located predominantly on the metal. So the charge transfer bands can be from the ligand, from orbitals from the ligand to orbitals to the metal, or from orbitals to the metal to orbitals to the ligand, or from orbitals having more metallic character to orbitals having more ligand character. So there are several evidences that can be used to identify a band as a charge transfer transition. The first one is the high intensity, so it has much more intensity relative to transitions between the d orbitals of the metal, which are often called or often named DD transitions. Another indication is that this band changes if we replace the ligand, and as these bands are strongly dependent on the nature of the ligand. So these differences in intensity between bands, DD bands or DD transitions and charge transfer bands raises the question, like, why do we have these differences in the intensities of the absorption bands? So if you have an octahedral or square planar complex, for example, the maximum absorption coefficient, which is a measure of the strength of the absorption, is typically less than or close to 100 cubic decimeters per mole per centimeter. For tetrahedral, this value is 250. And for charge transfer band, this is much higher already. And these intensities of these bands are actually dictated by selection rules. And this intensity refers to the strength in which the complex can couple with the electromagnetic field to generate this electronic absorption. So intense transitions or intense absorption bands indicate strong coupling, while weak transitions indicate weaker coupling. So the strength of coupling when an electron makes a transition from a state with an initial wave function to a final wave function is measured by this transition dipole moment defined by this integral. And this will dictate the intensity of the signal that is detected. And the intensity will be dictated, like we can guess or have an idea on the results intensities based on the knowledge of spectroscopic selection rules, which is a statement about which transitions are allowed and which transitions are forbidden. And here, when we say allow transitions, we are talking about transitions with a non-zero transition dipole moment and hence non-zero intensity. And a forbidden transition is a transition in which we have a transition dipole, which is calculated as zero. So one of the reasons why we have such a large intensity for charge transfer bands is that they are fully allowed, and therefore they lead to intense absorptions. Okay, so let's see now the transitions and why they are weaker relative to charge transfer bands. So the first selection rule is the spin selection rule, which indicates that the electromagnetic field of the incoming electromagnetic radiation cannot change the relative orientations of the spins of the electrons in a complex. For example, an initially anti-parallel pair of electrons cannot be converted to a parallel pair. So a singlet cannot undergo a transition to a triplet. So therefore, this means that for a spin allowed transition to take place, or for this rule to be the spin selection rule, shows that we can only have electronic transitions for which there is no change in the multiplicity of the terms. So no change in the multiplicity of the spin. So this is forbidden, for example. So the selection rule is that the variation in the multiplicity of the terms should be zero. So only transitions allowed are the ones in which there is no change in the spin multiplicity. And there is another selection rule, which is the Laporte selection rule, which rules that in a centrosymmetric molecule or ion, so molecules having a center of symmetry, the only allowed transitions are the ones that lead to a change in the parity. So for example, a octahedral complex is a centrosymmetric environment, which is an environment in which we have an inversion center. So if we go from one point to the molecule, passing through the inversion center to the similar point, passing the inversion center, we should arrive that the molecule remains unchanged. So if we go from each point of the molecule through the inversion center, we see that the molecule remains unchanged. So the molecule is centrosymmetric. So we have this notation of G terms. So the terms having the G notation are centrosymmetric, and terms having the U notation are non-centrosymmetric. So this means that a transition for a term centrosymmetric, a transition between two terms that are centrosymmetric or two terms that are G or have the G notation are not possible. And a transition between two terms that are U are also not possible. And so the only allowed transitions are the ones that occur between terms of different parities. Okay, but then you ask me, like, well, but in the octahedral complex, we had T2G and EG, those terms are G, right? In an octahedral complex which is centrosymmetric. So this is right, yes. So this means that in many cases, in a centrosymmetric complex, if there's no change in the quantum number, there's no change in parity. So in principle, SS, PP, FF, and DD transitions are forbidden by this selection rule, as d orbitals are G. They have this kind of symmetry in the octahedral environment. So, the interesting thing is that in a centrosymmetric complex, such as octahedral geometry, for example, the DD transitions are forbidden. And this forbidden character accounts for the fact that they have a relative weak intensity relative to the charge transfer band, and also to be more weak for an octahedral complex relative to a tetrahedral complex. And this is because tetrahedral complex is not centrosymmetrical, therefore this rule, this selection rule does not apply. So why we can still have DD transitions in octahedral complexes if they are forbidden? Well, we still have this transition because the selection rule can be relaxed in two ways, because the complex during movement, during collisions, they can depart slightly from the central symmetric symmetry due to asymmetric vibration, and also the complex cannot, maybe it's not like perfectly centrosymmetric, so not a perfect centrosymmetric geometry, or not perfect octahedral geometry. So either not perfect geometry or some distortions from asymmetric vibrations, for example. So here it is therefore a summary of the intensities of the bands for different types based on the selection rules for 3D complexes. Okay, so let's do a quick break now, and then after this we will discuss some reactions in coordination compounds. So let's get back at 1:19, okay? So a 10-minute break. So see you guys soon. So So welcome back to our lecture. So now we are going to talk about some common reactions that are observed in coordination compounds. Mostly, we will talk about ligand substitution reactions and redox reactions in this case. So the most fundamental reaction that a complex undergoes is ligand substitution, which is a reaction in which one ligand displaces another. So a reaction in which one Lewis base displaces another Lewis base from a Lewis acid. So this includes complex formation reactions in which the leaving group is a solvent molecule, for example, and the entering group is another ligand. An example is this replacement of the water ligand by chlorido ligand, as expressed here in this equation, in which we can have the chlorido replacing one of the waters in the coordination sphere of the metal to generate the corresponding complex. And then we can, these ligand substitution reactions can have different kinds of mechanisms. And then for the coordination compounds, we can have three different types of mechanisms. So they can be classified as association, dissociation, and interchange. So when we are talking about the reaction mechanisms, we are referring to a sequence of elementary steps by which the reaction takes place. In a simple sequential reaction scheme, the slowest step dominates the overall reaction rate and the overall law, and therefore this is the rate determining step. So when we are talking about coordination compounds, three classes of mechanisms have been identified: dissociative mechanism, associative mechanism, and interchange mechanism. So the dissociative mechanism, denoted as D, is a reaction sequence in which an intermediate of reduced coordination number is formed by the departure of the leaving group. So, so in this case, what happens is that here, when we have here metal Ln refers to the metal atom and the expectator ligands. So what happens is, if we are having here the reaction in which M is, in which Y is replacing ligand X in the coordination sphere of the complex. So in the dissociative mechanism, first there is the dissociation of cleavage of this bond with X, forming an intermediate with a lower coordination number, and then in the second step, the entering group binds to the metal. In the associative mechanism, we have that first the entering group binds to the metal, forming an intermediate having a higher coordination number, and then in the next step, the bond with the leaving group is broken and the leaving group is released from the molecule. And in the interchange mechanism, denoted as I, we have a single step in which the bond between the metal and the leaving group is broken at the same time as the bond between the metal and the entering group is formed. So the leaving and entering groups exchange places in a single step, forming therefore a transition state and not a true intermediate. So this interchange mechanism is very common for many reactions for 6 coordinated complex. So when we are talking about now the rate dependent step, we have to consider the rate determining step and the details of its formation. So the rate determining step can be associative if the rate depends strongly on the identity of the incoming group, because this means that the bonding of the incoming group to the metal atom is important. It's going to be, in this case, this associative rate determining step is very common for octahedral complexes, because this enables or allows for the formation of an intermediate with a higher coordination number. And evidences for this is the strong influence of the nature of the entering group to the rate of the reaction. So we can have a reaction with an associative mechanism having the rate determining step to be also associative if the attachment of the entering group to the initial reactant is the rate determinant step. And this reaction can be designed as AA here, showing that we have an associative mechanism with an associative rate determining step. A reaction now with the dissociative mechanism can be activated associatively if the attachment of the entering group to the metal is the rate determining step, or dissociatively activated if the breaking of the bond between the metal and the leaving group is the rate determining step. So for a dissociative mechanism asocially activated, it is denoted as DA. And if we have a dissociative mechanism which is dissociatively activated, then we have DD. So in this case, the rate will be independent on the identity of the entering group. So if we have an associative mechanism, this can also be dissociatively activated if the loss of the leaving group here in this step will be the rate determinant step. So in this case, we can also have this designation AD. All right, so talking about now the interchange reactions, in this case, we can have that it can be either associatively or dissociatively activated with these kind of designations, depending on the rate in which the metal and bond with the entering group is formed, or depending on the bond between the breakage of the bond between the metal and the leaving group. So if the rate determinant step depend on the identity of the entering group, this means that the rate determining step depends on the formation of this bond, and therefore we have associatively activation. And in the dissociatively activation, we will have no dependence on the nature of the entering group. So here is a summary of the different mechanisms: associative, interchange, and dissociative, and the activation that can be associative or dissociative activation in all cases, and here showing what would be the step that is determinant for the rates of this reaction. So for each kind of the mechanisms, we can have associative or dissociative activation depending on how the rates how the rate of the reaction is dependent upon the identity of the entering group, basically. So for associative activation, we will always have that the rate will be dependent on the nature of or on the identity of the entering group. And when we talk, so this was for ligand substitution reactions. And when we are talking about redox reactions, which are reactions in which there is electron transfer between two different complexes, we can have two main mechanisms, which are the inner sphere mechanism, which includes processes involving the transfer of atoms. So in an inner sphere mechanism, the coordination spheres of the reactants shared a ligand transitorily to form a transition, a bridged transition state, and the outer sphere mechanism, which includes many simple electron transfers, in which in the outer sphere mechanism, the two complexes, they come into contact, but they do not share a bridging ligand. And then in this case, the electron transfer goes from one metal to another by tunneling. So, okay, so for the talking about the inner sphere mechanism, the mechanism is represented here by these steps in the figure. So the first two steps is the formation of a precursor complex, which here in which the two complexes come closer in contact together. And after this, the formation of a bridged intermediate in which we have a ligand substitution reaction here for the second complex, leading here to a bridged intermediate in which one of the atoms is shared, one of the ligands is shared between the two metals. So there's this bridged ligand connecting the two metals, and then the electron transfer occurs between the two metals via these bridged ligands. This is followed by the formation of a successor complex and dissociation to give the final products. So the steps in these inner sphere mechanisms is the formation of the bridge, the electron transfer, and then the cleavage of this bridge. And the rate determining step, that can be any of these processes, but often is the electron transfer step. So if both complexes after the electron transfer, if they are non-labile or if they are relatively inert to ligand substitution reactions, they can it can be stated that the breakup of the bridged complex can be the rate determining step. For the outer sphere mechanism, this involves electron tuning between the two reactants. So there is no disturbances in the covalent bonding or inner coordination spheres. So there's no formation of this bridged ligand. So the complexes come into close contact, and then there is a change in the bond lengths and angles, and then electron tunneling occurs without sharing a ligand or without the formation of a bridged ligand. So the rate constant depends on the electronic and geometrical structures of the reacting species and the Gibbs energy of the reaction. And a conceptual starting point to understand this simple reaction, which is not simple, is this electron self-exchange, in which we can have redox between the metals having similar ligands here in this case, so hexa-aqua complexes of iron 3 and iron 2. So here in these mechanisms, the two species come together to form this outer sphere complex. Then there is overlap of the respective acceptor and diurnal orbitals to give reasonable tunneling probability, and then electron is transferred, and then these redox processes happen, and then this association or outer sphere complex then dissociates into solution again. So here are some rate constants for some of these redox reactions by these self-exchange species, for example, as described here for various species. So here is another representation. So we have, it's important to note that cobalt-2 and cobalt-3, for example, or iron-2 and iron-3 as well. So these species have like different sizes. So for species in higher oxidation number, bond lengths are shorter because we have shorter distances and shorter sizes. So it's important to note that for the reaction to take place, the formation of this precursor complex is required to increase the probability of tunneling, in which the bonds for the complex having cobalt-2 plus have to decrease a little bit, and the bonds for the complex containing cobalt-3 plus have to increase a little bit, so that we have this electron transfer to take place. So when the reactants have different bond lengths, vibrationally excited states with equal bond lengths, but must be formed in order for transitions for the electron transfer to occur. So this is a comparison between the inner sphere and outer sphere mechanisms for redox reactions in coordination compounds. And one of the last topics that I would like to mention in this course is organometallic chemistry, concentrated on D metals. This is very common in organic chemistry, this kind of notation. And then organometallic chemistry refers to the chemistry of compounds containing at least one direct metal-carbon bond. So since the 1950s, this field has grown into a very thriving area, because these complexes enable the discovery of new types of reactions, unusual structures, and several practical applications in terms of organic synthesis and also industrial catalysis. So when we talk about coordination complexes that we saw here in our lectures, they are normally charged with variable d electron count, and then they are soluble in water. However, organometallic compounds, more like in analogy with organic compounds, they are often neutral, have fixed d electron count, and they are soluble in organic solvents. So here are some examples of organometallic compounds in which we can see these unusual structures and bonding happening. So the D metals form a large number of organometallic compounds. Many different kinds of bonding modes have been observed, and unlike the coordination compounds, the organometallic compounds have relatively few stable electron configurations that corresponds to a total of 16 or 18 valence electrons around the metal atom. So this 18 electron rule, for example, as it's stated for 18 electron compounds, highlight the importance of pi bonds and the importance to understand the origin of the restriction that organometallic compounds only can be achieved with certain configurations. So if we have, for example, if we remember the picture of the ligand field theory to describe a bonding in a complex, we can see that we have 6 sigma bonding interactions that are possible in an octahedral complex. And then when we have p interactions, the bonding combination can be made with 3 orbitals of the T2G set. This leads to a total of 9 bonding molecular orbitals, which gives space to 18 electrons. So the 18 electrons, or the 18 electron rule, comes from the availability of 9 bonding molecular orbitals that come from the sigma and pi interaction in in octahedral complexes, for example. So this 18 electron rule states that when a metal complex has 18 valence electrons, it is said to have achieved the same electron configuration as the noble gas in the period, which means that all the bonding molecular orbitals are filled, while zero anti-bonding molecular orbitals are filled. So it's the highest increase in instability by the ligand field that it's possible. And some deviations can occur, for example, for square planar complexes in which we can have 16 electron species, because with strong field ligands, a square planar complex will have only 8 bonding orbitals. So in this case, we will have 16 electrons. So here is this a table summarizing the validity of this 16 or 18 electron rule for organometallic compounds of the D metals. So the metals that usually have 18 electrons, and then metals that usually have less, or metals that can have either 16 or 18 electrons. Because also it's important to note that some steric factors can restrict the number of ligands that can bond to the metal atom, and this could, some ligands can stabilize compounds with lower electron counts than expected. So some important ligands in organometallic chemistry is carbon monoxide, for example, that can form sigma interactions with the metal atom or ion in a organometallic compound, but also it enables pi interaction in which the pi orbitals of carbon monoxide can act as a acceptor of charge, so it's a pi acceptor ligand. Another is phosphines. So phosphines are also classified as organometallic ligands because of their properties, even though in theory there is no metal carbon bond, it's a metal phosphorus bond in this case, but they are also a very important ligand in organometallic chemistry. So they bond to metals by a combination of sigma donation from the phosphorus atoms, and also is a pi acceptor ligand as well, as described for the carbon monoxide. And here we have like some formulas and structures for some carbonyls of the 3D series, which can be classified as organometallic compounds. And regarding reactions involving organometallic compounds, we can have reactions involving gain or loss of ligands, such as ligand dissociation and substitution, oxidative addition and reductive elimination, nucleophilic displacement, also reactions involving modification of ligands, such as insertion and carbonyl insertion, hydride elimination, and abstraction. So addition reactions will lead to an increase in coordination number. Dissociation reactions will lead to a decrease in coordination number. Oxidative addition will lead to an increase in coordination number, with also an increase in the oxidation state of the metal, while reductive elimination will lead to a decrease in coordination number, as well as a decrease in the oxidation state of the metal. So here is an example or two examples of ligand dissociation reactions in organometallic compounds. So here we have carbon monoxide dissociation, and here we have dissociation as well, in which we have the ligand substitution of one of the carbonyl groups by phosphine. We can also have the oxidative addition, which is one of the most important organometallic reactions, and they are essential step in many catalytic processes in which we have the metal and the ligands here, and then we have a molecule binding to this metal. So in the oxidative addition, these two species are added to the metal atom, and there is an increase in the oxidation number of the metal here relative as a result of the addition of these species to the molecule. And the reductive elimination is the opposite step, in which the species X and Y leave the metal atom, and there is a decrease in the oxidation number of the metal. So these fragments are seized to each other when they are eliminated. So here we have an example of oxidative addition, in which we have that species here, methane here, is eliminated from the molecule. And there is a change in the oxidation number. So platinum goes from 4 to 2. And in the opposite direction, or the opposite reaction, is the oxidative addition. We can also have modification of ligands now, such as insertion reactions, for example, in which carbon monoxide or sulfur dioxide can be inserted between the metal and the original ligand present in the complex. All right, so these are like very briefly a description on the definitions and the bonding, some ligands and some reactions in organometallic chemistry. There are more advanced courses dedicated only to organometallic chemistry in the master's program, if you guys are interested in the future. There's also disciplines covering application, and this course also would cover applications of organometallic compounds in catalysis as well. And yes, so with this, I think we finished the description of all the contents that we were planning to do here in this course. So as I just mentioned, there are advanced courses in the master's program that goes into organometallic chemistry and reaction mechanisms. We also have in the master's program in materials research, so more courses dedicated to more in-depth description of solid state chemistry, which we just gave a brief introduction here in this course. So there is also more advanced courses in the area of catalysis as well, involving these solid state materials and also coordination compounds in the context of organometallic chemistry. And we also discussed in the beginning these foundations, or the chemistry of the elements, talking about properties, oxidations and reductions, and acids and bases, for example. And in the case of oxidation and reduction, this is the core of electrochemistry, and there are more advanced courses in physical chemistry and redox properties as well in our master's programs. So in this inorganic chemistry course, the idea was to give you guys the foundation and cover an introduction on all these several important topics in inorganic chemistry. And even though, because of the size of our course, we couldn't go into much detail into many of these concepts, many of these subjects are still covered in more detail in more advanced courses in the master's programs and more advanced courses in chemistry as well. So with this, we end our course, and then we will have our exam on Wednesday. So if you guys have any questions before the exam, please let me know. And if not, I will see you guys on Friday at 12:15 for the exam, okay? So I hope everybody is studying, preparing yourselves. There is still a homework due on Friday. So I will see everybody on Friday. So does anybody have any questions before we wrap up? If not, thank you very much, everybody. And then I will see you guys for the exam on Friday. All right? All right. Bye-bye.